or this means that you need to assume something about the beliefs of the evaluator about individual preferences. For instance, the evaluator could believe that all individuals have convex preferences, or stronger notions like separable and convex preferences. All this is within this general approach, and then we will discuss one particular assumptions on the beliefs of the evaluator, namely symmetry. And this symmetry condition will then lead to a very particular solution concept, the Tьюки median. All right, so this is just overview, and probably you cannot understand at this point, but just to manage your expectations, that's what I will talk about. So here is our motivation in more detail. So what we want to do is we want to do social choice in a majoritarian way, right? So we want to ultimately base our choices on majoritarian principles in a setting where we have uncertainty about individual preferences, right? So in contrast to the standard social choice model, where you assume that you know preferences of individuals, and then you have to find the best compromise between these known preferences. Here, the model is different. We do not have full knowledge of individuals' preferences, but we know something. And the question is, what do we know? First, and this we call frugal aggregation, we know by assumption individuals' top choices, right? So there is a space of alternative. Each individual does have a complete preference over all alternatives, but we, and by we I mean a social evaluator, the person or the one who has to make the choices, knows only the top alternatives for each individual. Now, if you think about that assumption, this is of course very weak. And I think if you know something about voting theory, you should immediately ask the following question. Well, all right, if I only know the top choices of the electorate, right, of the individuals, of the agents, what can I do? I mean, perhaps plurality rule, right? I mean, I just count which choice is named more often or most often as the top choice of the individuals. Okay, so if you literally know nothing but the top choices of each individual, not much can be done. So the model becomes interesting by this second assumption. The second point here, you see my cursor, right?
Yes.
So
Yes.
the first point is simply that we know individual top choices, but then we know something else. And this will be significant. And what is the something else? Well, we know that preferences have a particular structure. We do not know which individual has which complete preference, but we know, let's say, for example, the preference is convex, right? We perhaps know that each individual has convex preferences. Actually, this will be also our main application point. But at this point, we can be more general. We have some beliefs about these underlying complete preferences, and these beliefs are ambiguous. I will come to that point. What does it mean to have ambiguous beliefs? But the ex ante Condorcet approach now does the following. Well, as the Condorcet, as you would expect when we invoke Condorcet, what we do is give me any pair of alternatives and let me try to find out which alternative beats the other one by a majority. Well, if I have only ambiguous beliefs, then for some belief, one alternative would beat the other, and for some other beliefs, it would be the other way around. So what this model delivers, this ambiguous belief model or imprecise Bayesian model, is that a certain range of possible majorities. For each pair of alternatives, I have a certain range of how many people could prefer one alternative to the other and the other way around. But then this is a generalized majority tournament. Ex ante, it's uncertain what are the majorities, but there are possible majorities, and that I can compare. The possible majorities for X and the possible majorities for Y, I can compare for two alternatives, X and Y. The assumption is that the evaluator who has to find out about these majorities is completely ignorant, right? So I do have beliefs, but I do not know which belief is more reasonable than another. I just have a set of beliefs. Question, does this majority tournament then has maximal elements? And the answer is actually, in interesting cases, it does have maximal elements, though that is quite surprising. Okay, I'll come to that. Applications of the model are, let's say, budget allocation, participatory budgeting, where the space of alternatives, let's say, is a hyperplane, right? You have tax money. The tax money can be spent on different purposes. Individuals have different opinions about how the tax money should be spent, and then we try to find a compromise. That would be an application of the model.
Sorry, Clemens.
Yes,
may
sure.
I ask question?
Sure.
This very our absence of information about these majorities. When I make this decision about that this majority supports this or that majority,
Yes.
do I have some probability distribution in my mind that with probability 0.8, this majority might support? And
You will see. That's a very important point. I will come to that. I will explain it in
thank
detail.
you.
This is very important. This is a very important question. I will explain in detail.
Okay.
All right. So we will then investigate different assumptions about the epistemic state of the social evaluator. In particular, we will investigate the assumption that the social evaluator only knows that preferences are convex, that we call the plane convex model. And we will find out what will happen then, namely, the maximal elements in that case are simply the plurality winners, right? So, which means that going to convex preferences does not really give you much insights. But then we will impose a very natural condition, which we call symmetry. And together with the assumption that preferences are convex, the symmetry assumption will then deliver a beautiful solution concept, namely what we call the strict Tьюки median. So this is again some kind of expectation, raising your expectations. I haven't explained you any detail so far, and I will come to this after the relation to the literature. So what is very important to realize is we are not doing Arrovian preference aggregation. Why not? And not even Arrovian preference aggregation on economic domains, right? Why not? Well, because of the specific epistemic assumption that the social evaluator has imprecise beliefs about the preferences. That is the difference. Now, there is a relation to the standard spatial voting model, which has been used in political science very extensively. There, the assumption is that the social evaluator assumes that preferences are Euclidean preferences. So you have a top for each voter, and you assume that the complete preference is simply represented by the negative Euclidean distance to this top, right? So this would be a degenerate special case of our model, right? It would be the degenerate special case where you are sure that preferences are Euclidean. That's, of course, a very strong assumption. So we will relax that assumption considerably, but there is a kind of overlap with that literature. Notice, by the way, that in contrast to that literature, which produces only impossibility results, we have a possibility result here. So it's also very important that in contrast to all these negative results in the literature, we present a possibility result.
Mhm.
So, of course, there is a relation to a literature on preference aggregation under incomplete information. There is a survey article by Boutillier and Rosenschein. There is work by Jérôme Lang and others on this. Of course, there is also a relation to the literature on decision-making under complete ignorance. I really recommend every one of you to go sometimes back to this wonderful classic text by Lewis and Dreyfus, which is one of the really important textbooks in decision and social choice theory. And this is a wonderful book where this idea of complete ignorance has been discussed extensively. There are also newer contributions. In particular, Klaus has worked on this, not in the context of social choice, but individual choice. But this literature is relevant to us. And then from the point of view of application, really this participatory budgeting is important. And there has been a lot of interest on this recently. But now, after all this introduction, let me now come to the heart of the matter and answer Fuad's question. So I want to present you first the general ex ante Condorcet approach, and then I will specialize it to convex preferences. Okay, so we start with an abstract space of alternatives, X. Could be finite or infinite, it doesn't matter. It's an abstract space of alternatives. The social evaluator is assumed to know the profile of unique top choices, right? So for each individual, the individuals are indexed 1 to n here, right? The social evaluator knows what individual 1 to n would choose from these alternatives if they could choose alone, right? So they're top choices. But these individuals do have underlying complete preferences. I will sometimes call them ex post preferences, but there is no resolution of uncertainty, right? Ex post preference simply means the true preferences of the individuals, which I, as the social evaluator, do not know, okay? But, of course, I have beliefs about it, right? So the social evaluator is assumed to have a prior belief over the underlying profile of complete preferences. And this prior is called pi, small pi. Now, it is assumed that the beliefs of the evaluator are ambiguous. That means the social evaluator does not know which is the right prior to have. And this, for our purpose, seems to be a very natural assumption, because how should I form such a prior in the absence of any information, right? We have a nice result in the latest version of our paper where we show that, I mean, for instance, you could say, well, how about a uniform prior, right? So if I know nothing, why not have a uniform prior? Now, notice this is a prior over preference profiles, right? What would it mean to have a uniform prior? And in the latest version of our paper, we provide a nice impossibility result that there doesn't exist a uniform prior on the set of all convex preferences, let alone on the profiles of convex preferences. And the reason for it is, as just briefly, and then I will go on, that uniformity, whatever it means, in our context, it must mean affine invariance, right? Because convexity of a preference is an affinely invariant property, right? So every affine transformation of a convex preference is again a convex preference. So if a prior is to be uninformative in the sense of uniform, right, does not inject any more knowledge, it should be affinely invariant, right? And such a prior does not exist. So therefore, we cannot assume so easily that the social evaluator is Bayesian in the sense that the social evaluator has a unique prior. Priors are essentially non-unique here. So we have to account for this fact. So we consider a set capital pi of priors, right? So the set capital set is a convex set of priors, and the social evaluator does not know which prior is better than another prior, right? So there's just a set of possible priors, and that is then the epistemic state of the social evaluator. So the social evaluator knows the top choices, theta, and has a set of different priors over the complete preferences. Okay, so now come to Fuad's question. How do you do majority comparisons now, given this epistemic state? Well, as follows. Every prior small pi induces an expected majority for all pairs x, y in the following way. You have x, y. You ask how many people prefer x to y, and given any prior, you have an expectation of this, right? There is an expected majority for x over y given the prior pi. Okay? Now, if you acknowledge that you don't have a unique prior small pi, but a set of priors, you could ask yourself, what is the minimal expected majority under this set of priors? That's m minus, right? So the expected majority is called m for a given prior small pi. Now, for a set of priors, you ask yourself, what is the minimal number of people who could prefer x to y, given my set of beliefs? And what is the maximal number? So this is m minus and m plus. So in general, you don't have a unique expectation, but you have a minimal and a maximal expectation, right? So there is an interval of possible expected majority margins. Now comes the answer to Fuad's question. We define now the ex ante majority relation as follows. X, the alternative X, is ex ante majority preferred, given my state, my epistemic state, theta and capital pi, to the alternative Y, if and only if the minimal number under this set of priors who in expectation prefer x to y is at least as large as the minimal number of people who have the opposite preference for y to x. Now, you may think, oh, that's arbitrary. Why not take the maximal number of people who prefer x to y and compare this? And the answer is, unfortunately, it doesn't matter whether you take the minimal or the maximal number. Why? Well, because preferences are assumed to be complete. So if a voter or an agent does not prefer x to y, well, then he must prefer y to x, right? Okay, there could be indifference, but indifferences do not play a role here, as you will see in a minute. Okay, so I think that is one point where I should ask Fuad, is this an answer to your question?
Yeah, I got it. Yes, thank you.
Very good, very good. So now notice that majority intervals, right? We call these majority intervals. Let me go back. This is the majority interval here. It is characterized by the minimal numbers who could prefer x to y under my beliefs, and the maximal number of voters who could prefer x to y under my beliefs. So this is an entire interval. I will give you examples in a minute. Now, if you compare majority intervals, they can overlap, but they are unambiguously ordered. So if the minimum of an interval is larger than the minimum of the opposite comparison, then also the maximum must be larger than the maximum. So in the language of these ambiguity attitudes, the ex ante majority relation is independent of your ambiguity attitude, right? So ambiguity attitude would mean that you place more weight on the minimum or more weight on the maximum. If you put more weight on the minimum, you're ambiguity averse. If you put more weight on the maximum, you're ambiguity loving, and so on and so on. But this does not actually play a role here because it is independent of your ambiguity attitude. Okay, so to finish this general model, now you can ask, with this relation here, is it perhaps true that it has maximal elements? Is there perhaps an alternative X that ex ante majority dominates every other alternative? And the answer to this question is, well, you can define this set. And I think if you know social choice theory, you would say, well, okay, this set will be empty. We have all these impossibility results. So in many cases, we know that there do not exist Condorcet winners. Why should there exist ex ante Condorcet winners? But the answer is, there do exist ex ante Condorcet winners, even in cases where ex post Condorcet winners fail to exist. Right?
Sorry, Clemens, just
Yes.
understand. Because you construct this R relation R,
Yes.
on these very intervals, and then it will be interval order, right? Because you consider this intersection of intervals as indifference, and if one interval is more to the right than the other intervals, then you put this R. I mean, strict part. Then you get an interval order, and that is the reason why we might get Condorcet, ex ante Condorcet winners, maybe several of them, right?
No, it doesn't need to have the properties of an interval order. Notice that it is complete, right? It must be a complete relation, right? I mean, by definition, it is a complete relation. So either X is better than Y or the other way around. But
Okay. Yes.
the transitivity property, it does not, we do not know anything about transitivity properties. Right?
Oh, I see.
Not even interval order. So not even weaker notions of transitivity must be satisfied in general. But in some special cases, you will even get stronger properties like quasi-transitivity, right? You are right. You are right. You cannot expect to have full transitivity here, even under strong assumptions. But you can have quasi-transitivity. So the strict relation could be transitive, but that would be, you have to prove that. That is not automatically the case.
Oh, yeah, sure. This is necessary to prove. Then I just construct in my mind, sure, it should be proved, yeah.
Yes, we will come to examples now, actually. Let me give you simple examples. Well, first extreme case, but we have to understand also the simple extreme cases. Let us assume that you have unrestricted beliefs. So if you think everything is possible, right? What does the model, what does this ex ante majority relation give you? Well, you can only, if you know nothing about preferences and you compare 2 points, X and Y, well, for all tops that are different from X, Y, the preference could be either way, right? For all people who you know have a top different from X, Y, if you know nothing about their preferences, they could either prefer X to Y or the other way around. So in other words, for most of the voters, you don't know anything, right, about their preference. Or in other words, the minimal number that prefer X to Y could be 0. But except for one case. if you know that one voter has a top at X, you know it cannot be 0, but it must be at least 1, right? Because you know that there is one voter who has the preference top at X. Now, since we assume that preference tops are unique, if you have your top at X, you must strictly prefer X to Y. So you know there is one voter who prefers X to Y, okay? So in other words, if you compare any alternative X to any other alternative Y, you find that X is ex ante majority preferred to Y if and only if there are more agents who have the top at X than there are agents who have top at Y. Because all agents who have a top different from XY could have either preference for X or for Y. So they cancel out, so to speak. Only what you know is something about those agents who have their top at X. Okay? I hope that that is clear. If not, this is very important. So, but that means that in this case, where you don't know anything, you have unrestricted beliefs, you know that the ex ante Condorcet winners must be the plurality winners, right? So the maximal elements of this relation are clearly the plurality winners. So those alternatives who have more tops, the most tops behind them, okay? Of course, generically, when every voter has a different top, then you have many of these plurality winners. So it is not at all unique. It's a big set of ex ante Condorcet winners, but it's not empty, okay? So I hope this is clear. So in this case, you gain something. And what about convexity in a single dimension? Now, if your space of alternatives is R, let's say, or some compact interval of R, and you know that preferences are convex, this simply means that preferences are single-peaked, okay? Now, if you assume that the evaluator knows that the top of each individual and knows that all preferences are single-peaked, but not exactly how they look like, then you still have a solution here, namely the ex ante Condorcet winners are the usual medians. Why? Well, because let's say X is smaller than Y, you compare X to Y from the ex ante perspective, right? So what do you have to do? You simply have to look, are there more agents who have a top lower than X or higher than Y? All the agents between X and Y, you cannot say something about them. Why not? Well, because you don't know exactly their preferences. You only know their top is between X and Y. So single peakedness does not give you a restriction on their preference between X and Y. You only know that someone who is to the left of X will prefer X to Y, and someone who is to the right of Y will prefer Y to X. Okay? But notice that this information is enough to single out the maximal elements, because the median will beat every other alternative in this comparison. Actually, this is very important. I mean, this is not, this is a simple observation, but it's a nice observation. You can determine, if you know single peakedness, but not exactly how the preferences are single peak, you can determine the ex ante winner as the median without this knowledge of what happens in the middle between two given alternatives, right? This is I think it's not that deep issue, but it's a nice observation, right? I mean, you only need really to know the single peakedness as such in order to find that the medians must be the ex ante Condorcet winners. All right. So I think now I have set the stage for the true task that is here, namely, what is the counterpart of a median in single dimensions when you have multiple dimensions. So it is really about multidimensional social choice that we are talking about, because and then you have a problem, because you don't know how to generalize this concept of a median. And if you know a bit of the statistical literature, you know that there is a huge literature about multidimensional medians. And the question is, which one is the right one to employ here for our problem? And to give you a preview, why we do not end up with something that is, let's say, better known than the Tьюки median is that most of the multidimensional medians, like minimize the sum of Euclidean distance or L1 distance or LP distance, the problem with all these medians is they are not affinely invariant. Right? They require a coordinate axis and they depend on the coordinates that you have chosen. But what we need here is a coordinate-free notion of median, and that will come. All right. So let's now go to the multidimensional problem. How am I doing time-wise? Just a second. I get my
It's okay. Clemens, it's now 5:10, so
okay.
you have a lot of time. Go
okay,
ahead.
very good. All right, so now let's look at multidimensional problem, and let's focus on this application that we have in mind, the participatory budgeting problem. That is, you have simply a hyperplane, right? So here is the graphic picture of this. You have a hyperplane, you have an amount of money, let's say M. So this is the economic interpretation here. You have an amount of money M, tax money. You can use this for different purposes. Let's say infrastructure, healthcare, defense, whatever, what have you. And the question is, how do you want to spend the money on these different purposes, or let's say public goods? So there are capital L public goods. If L is 2, then you are in the one-dimensional case, right? Because you can then represent simply by saying, well, that's how much I want to spend on the first project. Then if you want to spend all your money, then you already know how much money you have left for the second project, right? So if L is 3, then you have a two-dimensional problem like here shown in this graph, and so on and so on. Now, people may have different opinions about how to spend the money. And notice that to ask them, I mean, there's also a motivation of simplicity of our approach. You would not ask anyone in this case for a complete preference ranking over all the different ways of how you could spend the money, right? You do not usually ask people for a preference ranking on all alternatives on this hyperplane. This is an extremely complex thing. You would not ask people about their complete preference ranking, but you would usually ask, what is your most preferred way of spending the money? And then you have only this limited information, the top choices usually. And then the question is, what compromise would you suggest, would you propose as a social evaluator? Okay. Now, suppose that the social evaluator knows a bit about preferences, namely that they are all convex. This makes a lot of sense to have convex preferences, because it means that if you, right, I mean, it's clear why convexity makes a lot of sense in this problem. Suppose you have a preferred way of spending the money, then convexity simply means the further you go away in one direction from this most preferred way, the worse for the individual, for the agent, but you don't compare trade-offs, right? So convexity here really means only that along a line that goes from your most preferred way of allocating the money, along that line, preference is decreasing. That is convexity. And this makes a lot of sense. It's not clear whether you can impose much stronger condition on the preferences. Okay, let's ask what happens if these are your beliefs. If your beliefs are people have convex preferences, but I know nothing else. Well, the unfortunate result is as follows. If individual tops, theta 1 to theta n, are in general position, so that no 3 points of these set are collinear on a line, on one line, then the result is still the same as if you had no information at all. Namely, you must include all your plurality winners in the set of ex ante Condorcet winners, right? And what is the reason? Well, if these points are in general position, convexity does never give you a restriction on preferences, right? Because you always compare points that are not on a line. So if one has a top, right, somewhere, theta 1, for instance, and you compare any two other tops, the theta 1 voter can have any possible preference between the other two tops. And therefore, this information convexity does not gain you anything, right? You're still stuck with plurality rule. Moreover, if there is a unique plurality winner, then you're sure that this must be the only ex ante Condorcet winner under convexity. Now,
Clemens,
yes.
I have a question.
Yes, please.
If I understand correctly, this condition that no 3 collinear,
yes,
does it mean that in general case, when I allow collinearity, then I might introduce some kind of weights to that very collinear things, and then maybe the same theorem will work?
That's right.
Right? Okay.
So if you have
collinearity,
yes, if you have collinearity, then you can say more. But let's say, I mean, from a perspective of application, collinearity is a zero probability event.
Yeah, that's right.
Yes. Yeah. But we will come to that. So there is, so this is, the result says, I mean, generically, because of the general position restriction, you still have plurality rule. And now this is, I mean, this is counterintuitive, right? You put so much knowledge now in the model, namely knowledge of convexity, right? That the question is, why does it not reflect somehow in the ex ante Condorcet winners? And this is what we call the conundrum. And now this is probably the most important slide for you here, which I want to present you now. I want to convince you that you should know something more than convexity. There is something more that we should impose other than convexity. But the condition that we should impose is of a different kind. It is not that we know something about preferences, but it's about, we know something about the correlation of preferences, or rather, we should impose a condition that preferences are uncorrelated, okay? All right, so this I want to explain now, and this is really the most important slide here. Consider the following situation. You have a lot of tops in some neighborhood U here. Let's say you have randomly drawn them from a uniform distribution. And well, the probability that these are in general position is 1, right? If you draw from a uniform distribution, they will be in general position with probability 1. Now assume that there is another point called X, and assume that for some reason, I mean, just to give you the example, you know that there are 2 voters who prefer X, who have top X, I mean, right? Whose most preferred alternative is X. And there are 2 voters. Now you are in a situation where you know X is preferred by 2 voters, and these points here are the top of each, but each only of 1 voter. Now, plurality rule says what? Well, it says X is the winner, right? Is the plurality winner, because X has 2 voters behind him or it, right? Whereas each point here only has 1 voter behind it. But this is, I mean, this is absurd in some sense, right? I mean, if you have many people with a top here, and then you have a point outside where you just know, oh, there are two people who have this as top. Should you really choose X? I would say no, certainly not. But why not? I mean, and here comes now the important thing to understand. Why not? Why does our concept of ex ante Condorcet winner say X should be chosen? Because if you are literally completely ignorant about underlying preferences, then you can, for each voter, you can draw, let's compare Y to X. To say that X is the ex ante Condorcet winner is to say that X must be ex ante preferred to Y. Let's suppose Y has no top, right? I mean, it's just an alternative, but it is between this U neighborhood and X. Now, the fact that X is ex ante preferred to Y rests on the following construction. For each voter here who has a top here, you can construct a convex preference that prefers X to Y. Although the top is here, I mean, by drawing some very small ellipse here around X and any point here, you can draw the ellipse so that Y is not included in the ellipse, which means what I'm saying is for each point here, there exists a convex preference such that if you have top here in U, you still prefer X to Y. But no, yet, is this clear? I hope this is clear. You can do that for each top here. I can find a convex preference, very particular one, of course, such that if you have a top here, then you would still prefer X to Y, just because I can draw this in a very particular way, like draw ellipses, which are very flat, right? So that for each top here, X is still preferred to Y. Of course, I'm assuming that Y does never, if you draw a line between X and Y, you never hit some point here, but that happens with probability 0 anyway. Okay, so I hope the argument is clear. Convexity gives no information about the preference between X and Y, even if you have a top here. So unless you are really on the line with your top on the line between X and Y, I have no information, so everything is possible. So again, the only information that I can distill from this situation is that X is the top of two persons, so it must be the winner. But this is in a sense a bit crazy, right? Because it is so clear that the vast majority of people would rather be on the side of Y than on the side of X. So here is the analysis of this conundrum. I can construct very particular profiles that would give me that X is actually ex ante preferred to Y. But these profiles are completely unnatural in the sense that for each voter here, I have to find another very particular preference. So let's now solve this conundrum simply by saying where exactly the point here is should have no impact on what I believe about the preferences. Or in other words, I want to model now the intuition that the top of a voter does not give any information about the underlying structure of the rest of her preferences. Now, this is then the task, and this is now the symmetry assumption that we impose. So the intuition that we want to formalize is that tops contain no info about preference structure. Right? Now you should ask, what do you mean by preference structure? And the answer is, yes, now we need to have a parametric model. And the flexible workhorse which we want to employ is quadratic preferences. Now let's assume that we know not only that preferences are convex, but that they are in fact quadratic. Notice there is a good argument why you can do that, because quadratic preferences are simply the approximations of convex preferences when you take Taylor expansion to the degree 2, right? I mean, so you can approximate any convex preference by a quadratic preference, right? And that's our justification of doing this. Notice that quadratic preferences have very interesting properties. If you compare X to Y, and you know that all people have quadratic preferences, then the people who prefer X to Y and the people who prefer Y to X simply sit on opposite sides of a hyperplane that separates X and Y. Now, for Euclidean preference, this hyperplane is perpendicular to the line through Y and X. If you allow general quadratic preferences, then this line can have any slope, but it still goes through the midpoint here. So quadratic preference separate the people that's very important. Quadratic preference work as follows. If you give me two alternatives, X, Y, and you ask me, if I know that someone has a quadratic preference, where are those people who prefer X to Y in terms of their top? And where are those people who prefer Y to X? The answer is simply draw an appropriate line, right, through the midpoint between X and Y, and then all people who prefer X to Y will have a top on one side and all others on the other side. Now, this already gives you a good intuition of what's going on. First, we note the following. Quadratic model as approximation of convex model. The quadratic model, if you assume that the social evaluator believes all preferences to be quadratic, then this has exactly the same ex ante majority relation as if you believe they are convex in general. So we don't lose anything here. But of course, we also do not gain anything, right? We still, if this is true, what is here, then we still have the result that plurality rule are the ex ante Coндорсе winners, right? But now comes the symmetry assumption. Now, this is the second most important slide. Symmetry means the following. A prior pi on profiles of quadratic preferences will be called symmetric if my marginal, right? I mean, if for a given top theta I, the marginal prior on quadratic forms is the same for all tops, right? So if a voter I, it doesn't matter which top a voter I has, the marginal distribution of the prior pi on the quadratic forms that this voter may have is the same across voters, okay? Now, this is now a restriction on what I believe about different voters, right? So it is not a restriction on the preferences themselves, but on the correlation of the preferences that voter I may have and voter J may have. And the condition says they should be uncorrelated, right? There should be no information. If I have the marginal distribution of quadratic preferences for voter I, this gives me no information of this voter because this is the same for all voters. So, in other words, let us now look at the following belief set, namely, the social evaluator believes that preferences are all quadratic and symmetric in this sense. What are now the ex ante Coндорсе winners? And the answer is the Tьюки median. So, what is the Tьюки median? The Tьюки median is a well-known concept in multivariate statistics. It is well known to a certain extent. I mean, some statisticians know it well. Here is the definition. Okay. Think of theta, of the tops, right? That's the top profile, just of data points, right? You have data points in Euclidean space. And now you ask yourself, what is a good center point, right? Or what are points that represent these theta? The idea is for each point X, you define a Tьюки depth, is it called. And this is this number here. It's this, how do you call this kind of symbol here? So I will call it just depth, right? D, for me, it looks a bit like Germanic letters. Old German letters look a bit like this. But I think, okay, I don't know what the correct name is. But it's the following. For each x, draw a hyperplane through x and ask yourself how many data points are on this side, how many data points are on this side. Do this for all possible hyperplanes that contain x and take the minimum of those, right? So the minimal data points that are on one side of a hyperplane through x, right? That's the coordinate depth. Notice, for instance, if you have the data points here and you consider a point outside the convex hull, what is the depth? 0, because you can separate x by a hyperplane from all the data. So on one side, there are no data points, so this must be then 0. I will give you examples in a second. The Tьюки median is simply those points, they are not unique usually, the Tьюки medians, those points that maximize this depth function, okay? That's the Tьюки median. It has been invented or by Tьюки in 1975. Let me give you one example here. Look at the following example. There are 4 data points here. Here is 1, 2, 3, 4. Where is the Tьюки median? Well, it is the intersection of the 2 diagonals. Why? Because look, if you have draw a line through that point here, then you find that on each side of that point there are at least 2 data points, right? However, you draw a line through this point in the middle, on each side of the line, there must be 2 data points. But for each other point here, let's say here is a point, I can draw a line so that on one side, there's only 1 data point. If I go outside the convex hull of these 4 points, I can even draw a line so that on one side, there's 0 data points, okay? So this is the Tьюки median. It's a very nice concept. Let me give you, just before I go on, I want to give you, sorry, I jumped to an example. This is the example. Just to understand the Tьюки median, let us ask, what is the Tьюки median in this example here? There are 5 tops, 5 data points. Where are the Tьюки medians? Okay, answer, you have to draw these lines here, okay? So that, that you have this 5-edge, 5-vertex star. And where are the Tьюки medians? Well, these are the red shaded area. Why? Well, if you take any point inside this red area and you draw a line, you will always have at least 2 points on each side of the line, right? 2 data points, right? For every point inside here. But once you go out, let's say I take a point here, then again, I can find a line through such a point so that on one side, there's only 1 data point, namely theta 2 here, right? So I hope that makes the concept clear of Tьюки median.
Yeah.
This is a beautiful concept, I must say. I learned about it only recently, to be honest. So because I'm not a statistician, I've not heard about Tьюки median before.
I haven't heard about it.
Yes. And the disadvantage, I can tell you, what is the disadvantage of the Tьюки median? It is algorithmically very complex, right? So there is no easy way to compute the Tьюки median. There is no polynomial time algorithm for it. But that's the way the world is. I mean, some nice concepts are difficult to compute, and that's the reason why the Tьюки, or at least this is why I believe the Tьюки median is not that well known. Okay, anyway, it is, notice, this is now a very important remark here. The Tьюки median is one affinely invariant multidimensional median. Now, it is clear if you are on a line, the Tьюки median is just the usual median, right? I mean, just think of it. If all data points are on a line, right, then the midpoint, the median, will have half of the data point on each side, which is the maximum you can have, right? So the Tьюки median coincides with the standard median in one-dimensional case, okay? But it is affinely invariant. So right, it's clear what affine invariance means, right? If I do a affine transformation of data points, then the Tьюки median also affinely is, you have to transform it by the same affine transformation, and it will be the Tьюки median of the transformed data points. But this is not true for most of the other multidimensional medians. For instance, if you take the geometric median, which is the minimum, the minimum of the sum of the L2 distances, this is not affinely invariant. If you do the same with LP distance, it is not affinely invariant. So there are only a few such concepts in statistics. There are also other medians than the Tьюки, but they are even more rarely used than the Tьюки median. And what turns out, and now comes the main result, this is our main theorem. For all profiles, if you have these symmetric beliefs on quadratic preferences, the strict Tьюки median is non-empty and it is the ex ante Condorse winner. What do I mean by strict Tьюки median? Okay, you need a refinement of the Tьюки median, so you have even a smaller set of solutions than the Tьюки median, but I don't want to go into that. This is rather technical. The important thing is that if you have a unique solution as ex ante Condorse winner, it must be the Tьюки median. In the case that you have several solutions, it is a subset of the Tьюки medians and a well-defined subset. All right. Do I have time for giving you the idea of the proof?
Yeah, why not? Yes.
Very good. All right. So here is
how much time you need. If you have a couple of
10 minutes,
days, then
10 minutes, 10 minutes, 5 minutes. I can do it in 5. Okay. So the first step, I mean, and this is not clear how this is achieved, but it can be achieved, is that the symmetric quadratic model induces the same ex ante majority relation as the uniform quadratic model. The uniform quadratic model is simply you fix one quadratic form and you assume that every voter has the same one, but you don't know which one. That's the important thing, right? So the uniform quadratic model is much simpler than the symmetric, but it's easier to analyze. But what you have to show is that it actually induces the same ex ante majority relation, okay? So this is much simpler. So now you believe that everybody has the same quadratic form Q. The only thing is you don't know which one it is. Okay. All right. So this is the first step. Then you show that under the symmetry assumption, this implies that the ex ante majority relation coincides at least locally with what we call relative Tьюки depth. Relative Tьюки depth is defined here. X is relatively deeper than Y if the minimum of data points that lie on half spaces that contain X but not Y is larger than the minimum of all data points that are in half spaces that contain Y but not X. Okay, that's a very natural way to do it. Observe that if you are that far, you have already solved the conundrum. Why? Well, because if you ask yourself, well, is X ex ante preferred to Y or not? What this tells you here, what you should do is draw a line between that contains X and Y and ask yourself how many data points are minimally on each side of this line. And the answer is here in this example, there are 3 here. So this means that Y is ex ante preferred to X because you can separate X from Y, let's say by a line like this, so that only 2 data points are down below the line, right? than above. Okay, so the minimal Tьюки, relative Tьюки depth of X with respect to Y is 2, but the minimal Tьюки depth of Y with respect to X is 3, as you see here, right? Whenever you draw a line between Y and you ask yourself how many data points are on one side of the line minimally, it is minimally 3, so 3 is larger than 2, so X is no longer an ex ante Condorcet winner, but Y is better from the ex ante perspective, if you know that this is true here. So this is already the solution of the conundrum, and we have to go on, and these are the 2 remaining steps here in the truth. Now you have to show that the strict Tьюки median coincides with the maximal elements of that relation that I have just shown to you. Okay, this is already some work. And then finally, you have to show that this set, the maximal element of relative Tьюки depth, is non-empty. And this is non-elementary proof. I mean, you need to have Zorn's lemma. So there is really something to do here. So, but that's the proof of the theorem, very briefly summarized. Okay, so let me conclude. Right, this I've shown to you. Perhaps we can talk about this later. So let me say that there are possible extensions of this, right? I mean, we can actually get rid of many of the concrete specific assumptions here, but what is important, and this is clear, is the symmetry assumption, right? My beliefs are such that I cannot extract any information about the rest of the preferences from the top information alone, right? So the top, the knowledge of the top does not allow me to infer anything about the rest of the preferences of the voter. Now, this is a symmetry assumption that we find in this context very plausible. And the result from this symmetry of beliefs is that we should employ this concept of Tьюки median. Now, in favor of Tьюки median, let me tell you a little bit more, but this is only 1 minute. Now, here in this picture, you may think, well, there are many Tьюки medians. The set of Tьюки medians can be very large. But notice, the more data points I fill in here, the smaller the set of Tьюки medians become. And if you have a continuous distribution, right, of tops, of data points, then it must be 1 point. It's unique, and it always exists. So if you have a large population, this is a very nice solution concept. I mean, for 5 people, as you see here, it is not single valued, as you see, and it could be a quite large error. But the more data points, the more voter come into this, the smaller becomes the Tьюки median and the solution. All right. I mean, from my perspective, that's it. That's what I wanted to
You
tell.
finished? Great. Thank you very much. I enjoyed it. Before you publish it, I enjoyed your results.
Thank you.
Now we come to the questions. Let me ask you, comments of question. First of all, do you know this McKelvey's theorem about dynamic voting in the space?
Yes.
Is it possible to reformulate this very his work, I mean his model, in terms of this? Then you see there might be the case, you remember that in McKelvey's theorem, everything might go outside of convex hull, etc., wherever in the space. And is it possible to reformulate in these very conditions, maybe to get this very result that it will come to this very red area? See, it will be very nice.
Yes, I think this is true. I mean, this follows more or less from our results. If you have this uncertainty about preferences and you assume the symmetry condition, right? I mean, it all depends on the symmetry condition, but then you would have the following result. I mean, actually, we have proved that already. You start anywhere, and then you do sequential majority voting. You will end up in the red area. It will converge. It will converge to the red area, and if you are in the red area, you will not come out of this area again.
That's great. You see, this will be very nice paper. If next time you see, promise me to come and give this paper.
Okay, I will. Yes,
seminar,
yes,
okay?
I will. I mean, I said that we have proved it. Of course, we haven't written that down in this way, but it should hold in. It must, in some sense, it must hold in this way.
Yeah, I think so. You see, because I studied Machiavelli's theorem in when it was published, 79, something like that. And at that time, I created another proof, so I know these details rather well, and I think it should work.
Yes.
And another question, which I think might be interesting, at the very beginning, when you came to this Tьюки median, you formulated several conditions or properties. You might consider it as a axiomatization of Tьюки median, but maybe that will be interesting, you see, to understand this. I don't know about this concept at all. I understand from where it came, but now I understand, you see. But maybe his initial assumptions or ideas were absolutely different, you see. So it might be interesting to get this, to make this bridge, you see.
Yes, very, very good question. And we have thought already about this direction, right? To give an axiomatic characterization of Tьюки median that does not, I mean, in some sense, you can think of this analysis as a sort of characterization of the Tьюки median as ex ante Condorcet winner. But it's not clear whether everybody would consider this ex ante Condorcet as an axiom. But you are completely right. There must be much simpler principles, like one would be affine invariance. Yeah. The other one would be that you should want to have the standard median in one-dimensional case. Question, what do you need else in order to have the Tьюки median? That's a very interesting question. And we have been
Clemens,
been thinking in this direction.
Yeah, Clemens, if you formulate it in terms of Condorcet winner, statisticians will not read it.
Exactly.
But if it is in terms of mathematical things, then it might be very interesting. Yeah.
So yes, you're completely right. So the one way to view our results is as an economic foundation of Tьюки median, but axiomatic characterization would be something different, right? It would be something that you could really present as statistician, and we're looking for that actually. But we have that's a kind of different problem than the one.
I'm not sure it's a different problem, but
it's very
from my point of view, there is an answer in your constructions. That is
hopefully
great.
Hopefully yes.
That's great. Thank you very much indeed. Okay, other questions and comments, etc. Please.
Yes, about an algorithm to find Tьюки medians. So as I see, so you just need to consider all pairs of alternatives and mark all half planes that has lowest difference. So here
that's right. Correct. It's correct.
Yes, and so there is no problem with exponential number of these half planes.
Yeah. The problem is, however, that the half planes, how do you parameterize the half planes, right? You must look for all possible half planes, and you must look for all.
But not all possible, just half planes are defined by pairs of these points.
That's right, but still, you need to consider all half spaces that separate two given points, right? You have x, y, and then you must consider all half spaces that separate those 2 points. But there are infinitely many of them. That's the problem. That's why it's algorithmically so complex, right?
Mhm.
So if you look at the picture that is just on my slide now with the pentagon, right?
Mhm.
Now, in order to check the Tьюки depth of any point in the plane, right? For instance, let's check the Tьюки depth inside this triangle here.
Mhm.
You really have to look at all the half spaces that separate, right? That contain such a point, and ask yourself how many data points are on each side. And there's no way, right? There's no way to have a finite number of half planes only to check.
Okay.
You have really to check all of them. That's a problem. So at least, I mean, I don't want to exclude that there can be an algorithm, but I haven't, in the literature, there's no algorithm known, right? But it would be, that would be an interesting thing. And there are now programs, I think, in the internet available that do computations like this, but they all rely on some simplifying assumptions and so on. So it is, I think, an NP hard problem. It's an NP hard problem.
Thank you. Okay, other questions, please.
Well, I have a question.
Yes.
I know that there are other, in special voting theory, there are other median concepts, and namely the concept of the heart came to my mind, and I wonder whether you
Which
were heart. This is a sequential median. If you draw all possible coordinate systems, then you can simply project the points on all the coordinate lines one by one dimension, and for each dimension you can compute the corresponding value for the coordinate of point, which will be included into the set of the generalized median, and it's called heart.
Clemens, as far as I remember, it was introduced by Norman Schofield.
Okay.
So
But
I wonder if you compare this other median concept with you, because it seems to me that it also satisfies the affine invariance.
Really, does it? Is it how is it different from simply the coordinate-wise median? So if you just take the coordinate-wise median in each coordinate.
Yes, but this is the coordinate-wise median when you consider all possible orientations of the coordinate system.
Ah, okay, I see. So if you consider all possible orientations, right? I mean, this is actually interesting. Could you? I don't know this concept. Could you write me the reference for this concept?
Yeah, I knew, because I read a paper on this concept, and it was proved there that, as I can recall correctly, that the heart is included into the uncovered set of
Okay, so
there was an article, Clemens. There was an article by Norman Schofield years ago, 80s, 86, something like that.
All right.
In which he discussed several concepts, and I think he introduced this idea of heart.
Okay.
Because this Tьюки median actually sounds very much like the heart.
Okay.
So you can just in order to get the independence of the orientation of your coordinate system, you just consider all the possible rotations of the system, and for each orientation you pick up the point, and the set of these points is exactly the set of which is the heart.
This is very interesting.
Maybe the Tьюки median set is exactly the heart in maybe two-dimensional case.
Okay,
that's a good point.
could be. So I would be very grateful if you could send me a reference on this.
Andrei, you know, do you know this very reference? I will try to find. I try to find.
Well, I refereed a preprint of
technical
Alexei
time.
Zakharov
Okay.
many years ago on this.
Okay.
It was published in our series of preprints.
Yeah, but Alexei, I know, but I think I will find it Norman's article. I think
I think in the preprint we can also find a reference for the original definition.
Yeah.
So if you can send me the preprint, I would be very grateful.
Okay, I will send you then this reference. Okay, great.
Yeah, great, thank you. Actually, we were also thinking about exactly this, right? That you want to have a median independently of your coordinate system. So what you should do is you should, and that's how you can interpret our results, you should be completely ignorant about the coordinate system, right? So you want a concept that is independent on how you specify coordinates, right? So this sounds very much like what you're telling, right?
Yeah.
Very so good. It would be very interesting to check this. Yeah.
Very good. Okay, other questions, comments, ideas? No? Clemens, I do thank you very much for your presentation. I sat here and this whole time I enjoyed very much what you did. And tell my hello to Klaus.
I will definitely.
And we will try to find these very references and send you.
I have found, so it is.
Yeah, go ahead. Sorry?
Yeah.
Sasha, yes, please.
The heart I saw in chat. I think it's this. Yes? The heart and covered set.
The heart and the uncovered set.
Put it in
I think it is that one.
So I did not open it, but
okay.
Possibly it is it.
Yes.
Possibly.
Thanks so much, Alex. Very, very good. And
great.
The uncovered set, okay. Journal of Economics. All right. 1999.
But you can easily find it because you see we have in the Institute of Academy of Science, in Institute of Control Sciences, we have a rather very huge not database, even you see like a library of these articles, reprints, etc.
Okay.
So my idea was to find it there, but you see, Sasha found it.
Yeah, but if you have, I mean, I would be very much interested in citing a working paper of your institute, right? So
yeah,
if
I will send you.
Working paper, please do send it to me.
Okay, I will send you, yes.
Thank you.
Sure.
All right, so let me thank you all for your attention. I would have loved to, as I said, to see you and chat more with you in person, but next time we will do that.
Next time, Clemens, we are, first of all, we are waiting for you here. And second, this very extension of these very things to maybe Markelvi theorem, maybe to median, etc. Thank you very, very much.
So,
okay.
Thank you. If you are going to Paris this July, then we can probably meet at the Social Choice and Welfare Conference, which I am about to attend.
Please, everybody who now listened, I will be in Paris, and I will be very happy to speak to everybody there in Paris.
Okay, good.
All right.
Bye-bye.
Bye. Thank you.
Bye. Thank you very much.